Welcome to a new video. It's Federico here, and today we're going to see how to create, how to sonify a particle system. So first we will create a very simple particle system, and then we're going to sonify the particles using MC objects in Max MSP. So if this looks like something interesting, keep on watching, and let's dive right into it. So let's start. And what I've got here is just my Jitter world with a camera and anim dry, the usual setup. And what we're going to do next is to create our particle system. Now, this is going to be a very simple one because we're just starting and I want to start simple and then we can build on top of this. So first thing we need is definitely a Jitter matrix. And this will decide the number of particles we want to have. First of all, how many planes we want to have. Let's say we want to have 3 planes for the velocity and the position of our particles for the x, y, z components of these of the position vector and the velocity vector. And then let's say we want just 10 particles, 10 tiny particles. Cool. And then we need a JIT_gen. This will be where our all particles logic is built in. So let's give it a title and call it particle logic. And then we need another matrix here, which will have the same name of this matrix. So this matrix will be called position. And this matrix as well will be called position. Actually, we just need the name. We don't need the other arguments. Because this will allow us to have the loop necessary for the particle system to work. Now, if this is not clear, I have a tutorial exactly on that, which I will link in the description. So if this was not clear, just go there and watch that tutorial. Cool. So once we got these in place, we just need to bang these matrices continuously. So for every frame, we need a bang, and we can do that connecting the top matrix to the metro, to this sender metro, which gives us the bang from the Jitter world, the render draw bang, which is a different bang for each frame. And then we need to visualize those matrices. So for that, we will use a GGL mesh object. And we want to give it draw mode points. Draw mode points. And let's connect this here. Let's maybe give it a bigger point size. So point size, let's say 10. Okay, and there is our particle. Our first particle is being created. Let's make it white. So we give the color attribute to our GGL mesh. So color 1111. Nice. Let's make it bigger. So point size 20. Okay, there we go. Now, it doesn't matter if we are closer or farther with the camera, because the draw mode points as it is will not care if the camera is close or far. In fact, we can actually just delete the camera, go in our Jitter world and actually just work in 2 dimensions. So we can set ortho to 2, which means orthographic projection without any sort of depth. Okay, so now we can start with our particle logic. So inside JIT_gen, we want to move these particles. And to move this particle, we can do like this. Every frame, we can sum a little value to our position vector. So this will be our force, let's say. And let's sum a force that will bring our particles up of 0.001 units. And if we do that, we can see that our particles is raising and is starting to go up. Very cool. At a certain point, it will just go beyond the screen. So if we make this go faster, like 5 times faster, you can see that it will just go beyond the screen and it will be lost forever. So one thing we can do is to just wrap the position of this particle between -1 and 1. What does it mean? That every component of the position vector will be wrapped around -1 and 1. So if a component of the vector is greater than 1, it will go back to -1. And if a component is smaller than -1, it will be wrapped to 1. So in this way, the particle will go above 1, which is our epsilon limit, and then come back from -1 on the epsilon axis. This will work as well for the x-axis, but at the moment the x-axis is not being modified. If we modify the epsilon axis as well, you can see that it will work as well for the x-axis. And you will see that the particle will come back from an x value of -1. So we could draw the outline of our world with a GGL grid shape, maybe with a shape plane and just dimension 2 by 2. and this will give us just a square. But if we say poly mode 1, 1, we will have two triangles. But if we give it the attribute grid mode quad grid, then we should just see a square. Okay, so let's hard code that. Let's go here and say grid mode 0. So it will just show a square. Let's give it the color of white as well. So these are the boundaries of our virtual world. Let's put it down here somewhere. So now you maybe notice that we have here 10 cells in this matrix, but we just have one particle floating. Well, these are actually 10 particles, but they are all in the same position. So they are all moving together, basically. So if we want them to actually not be all together, but be in different places so that we can see them, we can give them a different initial position. So we can do that with a JIT noise, 3 planes, float 32, and 10 particles. And let's just bang that. So if we take away now the X movement, we do that, you can see that they will all start in the positive quadrant of our world, the positive 0, because JIT noise just gives us number between 0 and 1. So what we want to do is to maybe use a JIT map and say map 0 to 1, we map it between -1 and 1. So now they will cover the whole surface of our boundaries here. Cool. And now you can see they are happily cruising through our 2D world. Cool. Let's now start to make some sonification of that. So, and to sonify those particles, we will use MC objects because it makes a lot of sense, right? Since those objects can have multiple channels. So, for example, we could have or maybe cycles. This is going to be a bit more nice for the ears. And we can give it 10 channels, so we can sonify each of one of those particles. And then we can use an easy DAC for the output, and we probably want an MC stereo to bring this down to 2 channels. Or maybe we should use the MC mix down. This is probably what we want to do. Mix down to 2 channels. And then we could use an MC unpack or something with 2 channels, so we can unpack this in our easy DAC. We could also use MC DAC, but I don't know, I prefer to just unpack that. Cool. So the mix down right inlet will be the pan. Now for the pan, we can definitely use our position as it is, basically. We just need to remap it, but for the frequencies, we need to do some conversions of numbers here. So let's create another JIT gen here, and we could get the position matrix that it's here. Oh, you know what? We can just copy that and use the same metro here to say, okay, first bang this matrix so that all calculations for the particles are updated, and then bang our position matrix here so we can get those values and use them for our sonification, since the content of these 2 matrices is exactly the same since they have the same name. So inside here, what we want to do, let's just switch the epsilon position, which is the only thing that is actually changing. So we want to switch the epsilon position. And let's say we can scale, since this is only going between -1 and 1, we can scale it between, let's say, I don't know, 100 and 2000. Maybe this is going to sound pretty harsh. So let's say 100 and 700. So we will have frequencies going between 100 and 700. Cool. And then to transform these into values for our MC cycle, we can use JIT spill. And we want to spill the plane 0, since we only have basically using one value from the particle position, and this is only one plane. So we just want to spill the plane 0, and then we want to say list length, it's going to be 10, because we have 10 cells in this matrix. And then if we open the MC wrapper help file, we can check how it works for applying several values to the single channels of an MC object. So for example, the apply values message is a way to send one value from a list to each individual instance. So this is exactly what we could use to send the values from our list, from our matrix inside the MC cycle object. So let's do like this, and let's say prepend apply values. And we have some mad noises. So I had to switch the recording method in order to be able to record the audio from Max as well. So this is what we get. As you can see, when we go with the meter to 1 here, it will distort, and that's because I forgot to give to the mixdown object the auto gain attribute, which will basically automatically rescale the amplitude of our output according to how many channels we have. So now it doesn't distort. Let's actually create here a MC gain for our audio, right? Cool. Now, what I want to do is to spatialize the sound according to the X position of our particles. So what I'm going to do is to, inside our JIT here, I'm going to create another output, not output 23, but 2. And I'm going to say, switch the X and scale it. Instead of being between -1 and 1, I'm just going to transform it into 0 to 1. I believe this is what... Yeah, exactly. This is what the mixdown object wants. Channel signal pan position 0 to 1. So what we're going to do is to create another spill here. And then instead of an MC cycle, we're going to create an MC sig with 10 channels. Prepend apply values. Exactly the same thing. And then I'm going to connect this here and connect this here. Okay, so now our sound should be panned out. So we can give a title to this JIT and call it like sound to sound values or something. I'm not sure the panning will come out through the record because it's recording the sound on a single track, I believe. Sorry, my bad. So you will have to try it on your own computer to have the effect of the panning. Okay, but this just gives us a continuous sound, which, okay, the frequency is changing, but it's not super interesting. Now, what I would like to have is like a more punctuating sound. So what I want to do is to have like particles appearing, going in one direction and then disappearing, and with them the sound as well will disappear, and then they will spawn out again after a certain point. So what we need to do for that is to have a lifetime. So we need to create a new matrix which will represent the lifetime of our particles, and we need to copy it for the feedback loop system, and then inside we need to bang it as well. So each frame we want to bang this lifetime, and we want to give it an initial value of just random value as well, between 0 and 1 is okay. So let's connect this here. Let's go inside our JIT here, create another input. Let's actually give it a comment so we can remember what this is about. This is our lifetime. And we need another output, which also is our lifetime. And then we connect this here and connect this there. Cool. So our lifetime will be a random number in the beginning. We actually just want a single one of those planes. We don't want to have the 3 planes. We just need a single number for that. And we can pass this here. But before we pass it to the next frame, we want to subtract a quantity from it, like 0.01. And then if we do that, we will see that basically this lifetime is going to be 0. Exactly. You can see that when we bang here, it will start at a random number between 0 and 1, and then we'll slowly go back to 0. Cool. But if we use wrap again between 0 and 1, we will have these numbers continuously looping between 0 and 1. So when a number goes to 0, it will come back as 1, and then will keep decreasing. Nice. So what we want to do now, let's stop moving our particles. Let's just have them like this. So we want to say that when a particle lifetime is over, so we can say, is this minor or equal to 0? So when this is over, then we want to give a random velocity to our particles. So for that, we can use the noise object. We will create 3 random values at each time the JIT_gen receives an input matrix. So 3 values because we have an input matrix with 3 planes. But these numbers are between 0 and 1, just like the noise object. So we want to rescale them between -1 and 1. And then let's maybe multiply that by something smaller, so that the particles will not go too fast. So if we now do that, you can see that the particles will only move when their lifetime is over. But what I actually want is that they keep moving in this direction at each frame. So for that, we have to have some sort of concept of velocity from the previous frame. So we need to add a new input, which will be our velocity from the previous frame. And of course, a new output. And again, this is all stuff that I've explained in my particle tutorials. So if this is not making sense, just check out the particle tutorials, which I will link in the description. So now we need to create a new velocity. Now the velocity here as well, it doesn't need to be initialized with anything actually. We are okay by having it with initial values of 0. What we need to do is to bang it each frame. So let's connect this here, and let's connect this here. And it's not the lifetime, this is the velocity. And then we can just copy it and delete everything that is not its name. Don't need the P window anymore. Cool, let's make this gen bigger. Nice, so inside here, inside our JIT_gen with the particles logic, this is going to be our velocity. Actually, the lifetime should be better if it was the input 3, but doesn't really matter. So the velocity is what is going to be summed to the position of our particles, and the velocity, it's going to be summed to these values. So if, exactly, and as you can see now the particles start moving. So if the particles lifetime is over, then the particles will have a new velocity. Otherwise, they will have a velocity of 0. So actually we should not sum it. We should just do something like that. So if this is true, send out if this is false, send out the velocity. If this is true, send out our random velocity. Exactly. Now what we want to do, since this velocity is not diminishing at each frame, it just keep going as it is, we want to add a bit of friction. So we could multiply, for example, the input velocity by something like 0.99. So you can see that the particles, they get their initial velocity and then they are slowing down with the time. Okay, so let's make this lifetime a bit longer. So I will detract a smaller value here to the particles lifetime. And also what I want is that when their lifetime is over, for them to span in a different place. So for that, let's get again this noise. And let's say, cool, if the lifetime is over, then span just to a different noise position. Otherwise, just keep going on, just go on with your position from the previous frame, right? This is what we want to do. It's getting a bit cramped here. Will be cool also to influence the color of the particles through their lifetime. So like if the lifetime is diminishing, the color should get less bright. And for that, we don't really need a new output though. We just need to use the lifetime matrix. We could use JIT_pack with 1 output, and we can say jump 4. So it will use the same plane of this input matrix to create a matrix with 4 planes. And then we could use this as the color for our GGL mesh vertices, which are our particles. Cool. The only thing is that now they will get black, which I don't like. And by the way, let me make them a bit bigger. Right. Yeah, I don't like them to get black and just stay black there. So for that, though, we just need to use the depth enable and say, we need to say blend enable 1 and depth enable 0. So now the object will use the blending, and looks like our particles disappeared. Okay, I made a mistake here because clearly the fourth plane of this matrix is always set to 0. So let's do like this. We don't even need the jump attribute actually. Okay, this is probably the dumbest way of doing that. There is surely a better way of doing this, but what I want to do is simply to use the same matrix for all the 4 planes of our output matrix. It works, it just looks dumb. So I just unpack the first plane into the into 4 planes. Cool. And now we got our particles appearing and disappearing according to their lifetime. Okay, let's see how this sounds now. It sounds a bit more interesting, but we get some clicks. So when the particle jumps to a new position, the velocity jumps to 0, and so we get some clicks. Now, what we could do is to use the lifetime to multiply the sound, for example. So let's do like this, and let's create just a MC.multiplier, I believe. I guess we need to say that he has 10 channels, so we can connect it here. And we can use the lifetime just like it is. We can say split, plane 0, least length 10, and then we can say apply values, I believe. So let's see if this works. Okay, no, I think that's the dumb way of doing that. I think I need another MC sig probably, and connect this to that. Let's get the cool meter thing for MC. Let's connect it here just to see if our amplitude is actually diminishing. Yeah, okay. So the amplitude is diminishing, but we still get clicks, because when the amplitude goes back to 1, then it will definitely click. So in order to fix that, we could use again here JitGen. Give it as a title amplitude values. And before we send the matrix as a list, we want to do something with our lifetime. So inside here, don't need a second input. We just want a single value. So we call width x. This will be our lifetime. Could, for example, just use the cosine of that. So the lifetime goes from 0 to 1 like this. And if we do the cosine of that, then it will just go, or the sine actually we want to do, so it will just go between 0 and then go to 1 and then go back to 0, but we need to multiply it by pi for that to work. So we say sine, and we want to multiply by pi, so multiply by pi. Let's see what we get. Okay, I think the clicks are gone. Let's check. Yeah, sounds like the clicks are gone. So that's pretty cool. Could actually use the same system for the appearance of the particles. So instead of just going them from 1 to 0, we can use the sign of the lifetime for their color. So the sign is only going to go between 0 and 1, right? So we can just, instead of unpacking that matrix, we can, instead of unpacking the lifetime matrix, we can unpack that. So yeah, now we got it. The particles are going to appear and slowly then disappear using a sine function for their color. Okay, nice. Let's just try to change the frequency. So instead of going from 100 to 700, let's go from 100 to 1700. And okay, it's very spacey. It's not directly pleasant. But I'm sure you can come up with better sound algorithms. Sound is not really my specialty, as you maybe know. And I hope this patch will inspire you to dig further in that direction. Okay, so this was it. You can get this patch from my Patreon if you don't want to recreate it following the tutorial, or if you just want to support the channel, that would be much appreciated. Also on Patreon you can download all my other patches that I ever shared, and you can also get in touch with me on Discord, and all of these for a little monthly fee, which you can, of course, cancel anytime you want. Cool. So thanks a lot for following, and I will see you in the next video. Have fun. See you soon. Ciao.